This meeting is being.
So welcome everyone, and this is Mudassar. Let's get started with our stuff. Last time we spoke about read repair and entropy. We understood a bit about quorum read, right? And read repair, quite a few things. Anyone has any questions or queries to discuss before we move ahead? Prominently inside the leaders replication part.
Yesterday only we were discussing about the difference between the Merkle tree and segment tree, isn't it?
Yeah.
Correct. So, okay, I'll just quickly share something. Maybe just give me a second. Okay, so Merkle tree is slightly different. And okay, I'm just taking help of the very simple one, which is our from the Geeks for Geeks. So that might slightly give some idea. Okay, so here I'm sharing this. Okay, so this is, it might be a very basic way, whatever is being done here. So if you look at this diagram here, in this Merkle tree, if you see A, B, C, D, these are actually the real values of whatever that block might be. And then the hash on the top of that A, so if you consider A as a leaf, so hash A maybe the one which is on the top is also a leaf actually. So maybe that's the only difference I would say, because usually in segment tree you don't have this two-layered structure, right? So I didn't find much change other than that. So everything looks almost the same.
So another level, that level is for what you say, hash of the leaf, right? And top to the top of it is the hash of these two leaves, right? I mean,
yeah. So so other nodes, all the nodes, even the leaves are hashes, but leaves have two nodes, one hash and one of the real data.
Original leaf, okay.
Right.
Original data.
Right. So if you look at the node structure, what they're showing here, maybe it's a very simplified version in Geeks for Geeks. So the structure node will also have a key and the value.
So yeah, like the rest, I'm finishing up my goals. I will be attending that.
Okay. So and then the rest of the things are almost the same. So not much of a difference.
Yeah, basically they're building a hashing layer on top of the leaf nodes, right?
Right.
Yeah.
So we were actually trying to understand what's the actual difference between a Merkle tree and maybe it's somewhat resembles a segment tree. So we're trying to understand what might be the difference, because the inner nodes already have hash values. That was for sure. In the segment tree also similar, something happens. But here there's only difference. So similar construction and as well as the structure resembles, I would say, a segment tree, isn't it?
I don't know much about the segment tree. This one I can tell actually. So basically you from A and B, right? Actually they calculate the hash of A and B, then based on these two hashes, they create a single hash, combining the hash zero, that bucket of hash zero, right?
Mm-hmm.
Either you add it up. Same thing actually. Every layer of the tree actually you keep adding, right? Now you pass on this Merkle tree. Now you want to compare the data between the two nodes, right?
Mm-hmm.
So let's say at the top hash actually, then comparing will be easier, right?
Mm-hmm.
You compare the top hash of the two data from two nodes. If they differ, actually definitely there is a mismatch. Then you can check actually, is it the left tree is mismatch or right tree is mismatch?
Right.
Okay, then that's pretty much it actually. So basically, after every comparison, you are removing a log n by 2 number of nodes from comparison.
Yeah.
Yeah, that's what it is.
Right. So search space actually also reduces.
Yeah.
So here I can see like a hash age there. On top of that, I can say hash 00, right?
Yeah, I think actually they're adding it or something. They're showing some representation of that. Basically, it's actually hash of a in that
Yeah.
node actually.
Key value pair they are showing actually 0
Yeah.
0.
Right.
0 is the key, 0 is the value.
So
hash of
0,
zero-
0 is key. No,
Yes,
A is
and other
key.
No,
is key
actually
and
they look at that numbering, right? So the hash 0 is actually the node name, right? The one above that. So under hash 0 there are two things: hash 00 and 01.
Mhm.
So they're showing it to easily understand actually, right? Hash 01 and hash 00 are combined in hash 0.
Hmm. Yeah. So that is a hash 0. Then you have two left and right, which is hash 0
Exactly.
0 and hash 0 1. Yeah.
Exactly.
Makes sense.
Yeah, don't get confused by what is hash 00. That's just a numbering to show actually how they are adding it up.
Yeah. You can represent it in any way, whatever you like. But yeah, this is what it is.
Yeah, if you go to the Dynamo paper, they have a very good explanation. of
Yeah,
this stuff.
that will be a more advanced, right? So I just wanted to have a very light
Okay.
version of it. Yeah.
Yeah.
Okay. Yeah. Thanks. Yeah. Good.
Thanks, Santosh. Thanks, everyone, for that. Okay, moving forward today with the quorums for reading and writing. So in the example for 510, we considered the write to be successful, even though it was only processed on 2 out of 3 replicas. What if only 1 out of 3 replicas accepted the write? How far we push this? So just for people in case they don't remember, this is the diagram. So I think so the 3 replicas were getting the values wherein this got 7, this got 7, but this got 6. So yeah, it was a bit of a gap. Right. So coming back, if we know that every successful write is guaranteed to be present on at least 2 out of 3 replicas, that means at most 1 replica can be stale. Thus, if we read from at least 2 replicas, we can be sure that at least one of the 2 is up to date. If the third replica is down or slow to respond, reads can nevertheless continue returning an up to date value. More generally, if there are n replicas, every write must be confirmed by W nodes to be considered successful. And we must query at least R nodes for each read. In our example, n is equal to 3. Okay. N is the n number of replicas. Then W is equal to 2. There were 2 nodes, W other nodes. I think this is the leader 1, leader 2 node. Then R is 2. We must query at least R nodes from each read. So it was at least 2. We must query at least R nodes for each read.
Yeah, so 2 plus 2, 4, right? Which is greater than 3. That means if 2 reads are there, and I mean, 2 nodes are for reads and 2 for writes, and you have only 3 replicas, that means one of them will be common for both read and write, right? Which will be.
But we were reading 3 replicas.
Yeah, exactly. 3 replicas are there, right? Out of 3, you have 2 read and 2 write. That means one is common, right?
Yeah, you're going to send it to everybody, right? Actually, you're expecting only 2 acknowledgements back.
Okay.
At least 2, yeah.
Yeah.
Okay. So this is more from an acknowledgement perspective, the number of R for the reads. And the same thing goes with the write, is it?
Exactly. So all the time, right? Read and write, actually, we parallelly send the read and write request to all replicas, but we are expecting at least quorum to be coming back. If the quorum is not coming back, then we can't proceed.
Okay. I hope everybody's getting it. If not, please highlight. So as long as W plus R, which is the write and read, is greater than the N, in this case 2 plus 2, 4, is greater than 3 nodes. we expect to get an up-to-date value when reading, because at least one of the R nodes we are reading from must be up to date. Reads and writes that obey these R and W values are called as quorum reads and writes. Okay. You can think of R and W as the minimum number of votes required for the read and write. Yeah, I think this is a better clarification. The R and W. See. Okay, cool. So that's the base rule that W plus R should be greater than N. Sometimes this kind of quorum is also called a strict quorum to contrast with sloppy quorums. Okay. See that later. So in dynamo style databases, the parameters N, W, and R are typically configurable. A common choice is to make N an odd number, typically 3 or 5, and to set W and R as E and AR equal to N plus 1 by 2, rounded up. Okay. However, you can vary the numbers as you see fit. For example, a workload with few writes and many reads may benefit from setting W equal to N and R equal to 1. Okay, I'll read that again. For example, a workload with few writes. The writes are few, that's why it is setting it to the number of nodes here. W equal to N. And many reads, few writes and many reads may benefit from the setting R equal to 1. Okay, R equal to 1. This makes reads faster, but has a disadvantage that just one failed node causes all the databases write to fail. Okay, this is a bit of a contrast. If R is equal to 1, we are basically saying that we are waiting to acknowledge read from one node only.
And this is correct, right? This is same as our synchronous replication in the regular RDBMS side, right? So basically, what we are doing is actually we write to all the nodes, right? Making sure that all the nodes are in sync, right?
Writing small nodes, right?
Right. That means actually all the nodes have same exact data. Then we read from any of the one of these nodes. We don't need call. Because at the right path, we make sure that everybody is consistent.
But from read part, it is not.
Sorry.
Okay, no, correct. Yeah, because it's written to every node, so from right part, it's consistent. Yeah.
Yes.
Makes sense.
So that has the same problem, right? Actually, if one of the nodes in the right path fails, actually the whole system is down. It cannot proceed.
But for these applications, we'll be using where consistency is topmost. What is it? Priority, right?
It's tunable, right? Actually, so we are. So here he's talking about a system that has very few writes, right? This is exactly opposite of Amazon's use case. Amazon has a lot more writes because they want the system to be always available for writes, right? Here our system has very few writes. Mostly it's a read-only system.
That means they don't care much about consistency, more about availability, right? For the Amazon.
The other way, right? Actually, so availability is very, very low here, right? If one node fails, right, then they can't accept any writes, but the reads can still work.
Yeah.
But that won't be that will be a stale in that case, right? If all the system, I mean, if it doesn't get written to all the replicas.
Yeah, then no more writes actually in that system.
No more writes. So if you want write consistent, then W equal to 1 and R equal to N, right?
Write consistent. Yeah, write consistent. Yeah, this is write consistent. Yeah.
Read consistent will be R equal to N and W equal to 1.
Yeah.
Okay.
So that is a very, very harsh situation, right? You write to any one node, right?
Yeah, and
you are expecting to all reads to come from every other all nodes in that quorum, right? Then if one node is failing, same situation happens, right? Your reads can never work.
So midway you'll have to choose something. Yes.
Exactly. Yeah, that is why they are doing this n plus 1 by 2 roundup.
So, but this statement, I get it. The reads are faster because the minimum number of acknowledge we want is just one. We just want one node to give us the acknowledgement. So we are happy with that. But here it says that disadvantage is that one failed node causes all the database writes to fail.
Yeah. So think about, right. What happens actually out of n nodes, one will fail.
Okay, got it. Now I got it. It's like the minimum acknowledgement is actually the number of nodes. So there are 10 nodes, it has to wait for all the 10 nodes. So even one fails, the acknowledgement overall will be a failure.
Yes.
Okay, got it. Okay. So, yep, there may be more than n nodes in the cluster, but any given value is stored only on n nodes. This allows the dataset to be partitioned, supporting datasets that are larger than you can fit on one node. We will turn to partitioning in chapter 6. Okay. So, the quorum condition, W plus R is greater than N, right? These are greater than nodes, allows the system to tolerate unavailable nodes as follows. If a W is less than N, okay, writes, acknowledgement writes is less than the nodes. We can still process writes if a node is unavailable. Agreed. Agreed. If it's less than N, one of the node goes down, it's fine. Out of 3, 2 can acknowledge, but it's less than that. If R is less than N, we can still proceed reads if a node is unavailable. Okay. If N is equal to 3, W equal to 2, R equal to 2, we can tolerate one unavailable node. Yes. Okay. If N equal to 5, W equal to 3, and R equal to 3, we can tolerate 2 unavailable nodes. Yes, that's perfectly correct. This is illustration 511. Here is here. Okay. Just put this on 2 different. Yeah. Okay. And right, that's that. Then normally reads and writes are always sent to all n replicas in parallel. The parameters W and R determine how many nodes we wait for. That is how many of the n nodes need to report success before we consider the read or the write to be successful. So this is our diagram for W plus R greater than N, where at least one of the replicas you read from must have seen the most recent successful, right? So read is here, 5 replicas. So R is 3, W is equal to 3. That means we can live with 2 nodes being down because we need at least 3 to be successful. So out of 3, if 2 are down, at least 1 can report success. Cool. If anyone is not getting anything, please open up and query out just in case. So that's W plus R greater than N. Cool. Moving on. If fewer than required W or R nodes are available, writes or reads return an error. A node could be unavailable for many reasons because the node is down, crashed, powered down, due to an error executing the operation, can't write because the disk is full, due to a network interruption between the client and the node, or for any number of other reasons. We only care whether the node returned a successful response and don't need to distinguish between different kinds of nodes. Moving ahead, limitations of this quorum consistency. So if you have n replicas and you choose W and R such that W plus R greater than N, you can generally expect that every read to return the most recent value return for a key. This is the case because set of nodes to which you have written and the set of the nodes from which you have read must overlap. That is, among the nodes you read, there must be at least one node with the latest one, at least one, right? We need to have at least one node to be latest if the read is happening, let's say from these 3. So maybe 1 or 2 can be down, but 3 has to be running. Or if we are doing from this 3, 4 and 5 could be down, but at least 3 should be running. So in that case, at least 1 should be available with the latest value. That is. Often R and W are chosen to be a majority, more than n by 2 of nodes, because that ensures W plus R greater than N. Okay, while still tolerating up to n by 2 nodes failure, but quorums are not necessarily majorities. It only matters that sets of nodes used by the read and write operations overlap in at least one node. Other quorum assignments are possible, which allows some flexibility in the design of distributed algorithms. So in our case, if we take this example of 5 nodes, here if R and W are chosen, it should be more than n by 2. N is 5 in this case, so it's most like 2.5. So it should be more than 2.5. So yes, that is why it's 3 and 3. Right? So that at least 3 should be there for minimum acknowledgement. And one at least should have the latest value among those 3. Right? That's the whole idea of n by 2 over here. Then you may also set W and R to smaller numbers so that W plus R equal to less than n. That is, the quorum condition is not satisfied. In this case, reads and writes will still be sent to n nodes, but a smaller number of successful responses are required for the operation to succeed. Let's understand this. W and R is set to smaller numbers so that W plus R is less than equal to the number of nodes. So in this case, if it was 3 plus 3 plus 6, 6 is greater than 5. So here I'm looking at less than 5 or equal to 5. So either 3 plus 2 or 2 plus 3. So it is not satisfying.
But it will give you stale data also, right? At times, W plus R less, okay, equal to n. Yeah, it can give you stale data also.
Data,
right?
it depends. If my R is 2 and from the 2 nodes, if one is latest, it will work out.
Yeah,
No,
you can get the stale data. Yeah, because why W plus R greater than N? Because at least one node is overlapping from the old and the
Yes.
new data. Right? Yeah.
But here, if you have 4 nodes, you can have 2 writes and 2 reads, and both of them, I mean, none of them can overlap. So there's
Exactly.
chance of.
Yeah.
Makes sense.
One node needs to overlap. That is the whole idea. Okay.
Correct.
Yeah, but there is an advantage to that also, right? Yeah.
Yeah.
But always you will get a data. There is no chance of getting.
So what does this mean? But a smaller number of successful responses is required. Smaller number.
Like even few of them, your writes is written to few of the replicas. That is, you'll get an acknowledgement, right?
So if you go back to that diagram, right, it's easy to understand from there. So think about replica 3 is not there, right? And we have only 4 nodes in our quorum, right? So your successful, so your read quorum is 2 and write quorum is 2. So your write goes to replica 1 and replica 2. So, and it got the acknowledgement back. That means actually write is accepted. Now again, you're coming back to read. Your read is coming back from replica 4 and replica 5. Because that also is successful because you got the quorum back.
Yes.
Now your recent data is in replicant 1 and 2, and now your read came from 4 and 5. You see the stale data, right?
Yes.
Yeah, that's the problem with actually if there is no overlap in the read and write.
But at times you can get updated. Let's say that those read went to 1 and 2 only, then you will get updated. But there is no guarantee.
There is no guarantee. That's the problem, right?
No, I understand that you may get inconsistent data, but I am specifically interested in that line which is highlighted, right? Like what exactly does that mean? Like what is the author is trying to say by saying that, what was that line? But a smaller number of successful responses is required for operation to succeed.
Yeah, that is what the W and R, whatever we have said, that many number of responses are required for the operation to succeed. That is what Eric said just now, right?
That means you don't need to write to all the replicas. Even few of the replicas accepts the write, that would be considered successful, right?
Exactly. Even if actually, yeah.
Oh, so it is just
just
discounting the fact that if you are okay with like inconsistent data, then you can set it to lower number, right? Is that the right understanding?
Exactly. Yep.
Yes.
Yeah.
Still, you can
Because
say.
you have an advantage, on that, because you'll have a good latency, higher availability, and all that stuff.
But it's
Yeah.
to run a system like that, right? Because people will be really confused, right? Let's say you're watching the score of a game, right?
Mm-hmm.
Right now you saw 2-1 as the score for some football game, right?
Mm-hmm.
You refresh the screen, you see at 0-0,
Mm-hmm.
right? See, that's the problem, right? Stale data, I don't know how many systems.
But see,
those kind
in
of
this quorum, will you get? I got your point. Like you are going back on your the previous values, right?
Yeah.
So will that happen? See, if we have overlap of W and R with a node which has the latest data, at that time it will do a read repair.
Oh, exactly. So if as long as there is a overlap, you don't have any issues.
Right, right. But if you the guy who is reading will always get the stale value.
So sorry, say it again. Last part.
So because see, you had written on 1 and 2 replica, and if you are reading for 4 and 5, you'll always get the stale data.
No, he is not consistently reading from there, right? So his first request goes to replica 1 and go to read, right?
Okay, yeah,
Then
yeah.
So,
Yeah, got it. Yeah, but then in that case, anti-entropy may kick in, and then it might actually update the replicas, then you will get it.
yeah, not all this. Okay, so read.
Yeah, it won't happen always also, right? Yeah,
Yeah.
Because it will happen periodically. Yeah.
Yeah,
So there
exactly.
is a chance you'll have those problems, correct? Yeah.
So where do we use these systems? Like, I mean, what, Facebook and all? I don't. That's fine there, right? Even stale data, if somebody reads, it's okay, right?
No, actually, Facebook has strict policy, right? Facebook normally follows this read your write consistency, right? So they try to pin you into a replica, actually, into a data center, because normally your reads will normally go to that replica 4 or 5, right? At least for what you have written. So
you should be able to.
Yeah, exactly. You made a post and you go back to your home page and see. If you don't see the post there, you will be confused. So then they make sure that actually you will always see what you have done. But read your own rights actually. But for your friends, actually, they don't care about it. They can have some lag.
Even if it is deleted, it's fine, right? Nothing.
Yeah, because they have to. You have to see. You have to see the time moving forward, right? Let's say you saw your friend's post right now, but after a refresh, you shouldn't be seeing there is no post. If you saw your friend's post, you should continually seeing that. That is another guarantee.
Even if you don't see, that won't cause much of. I mean, it's not.
Yeah, there will be a user experience issue. But see, an example of this would be something like if there are sensor data for temperature, So if the temperature is going here and there, if the temperature is so sluggish, it doesn't matter if you get a stale value for some time.
Correct.
You won't be able to come to know about those things. Yeah,
Those are time sensitive values, right? I don't care about what happened previous value. I'm always interested in the latest value of the temperature, right?
Correct. TSD, time series.
What is the name for this phenomena which you just explained about? Like, if you have written a value, if you have seen a picture, the post should not go. So it is translated to repeatable read, or what is that name?
I don't quote me on this. Actually, it's called prefix read or something. Actually,
or read others, right? Something.
Okay.
No, yeah, prefix read. I believe it's called prefix read. Actually, I can also take a look. What does that mean?
You got my question, right? So in terms of consistencies, this translates to I think right. You just said right, like.
Read your right or.
No, like you posted something and after some point of time your friend says like there is a delay. So that's eventual consistent only, right?
Yeah, that is
No,
eventual
no, no.
consistency.
So no, yeah, eventual consistency is different, which is basically, I mean, you don't have any sort of guarantee, right? So this one is like if any of your friend has read the post is there, then the others will also see ahead of that time. Like if anybody is also seeing at the same time, and if anybody has seen like the post has been there up, so now nobody else should see that the post is not there. Like
E-
something like that it translates.
ex- Exactly. Yeah. So basically, not everybody. Let's say you guys are all my friends, right? And
Yeah.
only one person, right? Actually, let's say Santosh only saw my update. So rest of you guys didn't see anything. Now, when Santosh refreshes his screen, right, then Santosh should always see my update. It shouldn't see that actually it got deleted. If it is deleted, it's deleted. But actually, let's say Santosh is refreshing the screen 5 times, right? All the time, if
Mhm.
the post is still there, actually, he should be seeing that. Rest of you guys doesn't matter actually. You didn't see my post yet.
Oh, okay. I think then I have a other definition in my mind because
So are you
I
saying
was
that go back in the time, something like that? So because
Yeah,
if I
you.
see his
yeah,
post,
it is like if anybody has seen the latest data, then every other client also is bound to move ahead. Like they if they do the read at that t time, right? T delta t time, they should not see an older value than what the previous Santosh has seen. So something like that.
Yeah. So basically, if everybody wants to see the updated data, that means actually it's a strong consistent system, right? So that we cannot guarantee. So only what we can guarantee is actually none of the clients should see time going back, right? If you see something now, actually you shouldn't be seeing t-1. Everything should be t
Yes,
plus.
yes, yes. Mhm.
So that will happen only if you are reading from the same server, right? If you are reading from after refreshing, if your request went goes to the other server, you won't be seeing like the you can see the time back data, right?
Yeah, so there are different ways to solve that, right? So let's say Santosh saw my post, right? And so Santosh got a transaction ID, right? Like x equal to 10 or something. Next time when he reads something from any replica he gets connected, right? He will show this transaction ID x equal to 10. That replica knows that actually whether what's my last transaction ID. If it is less than 10, that replicant can reject Santosh's request because it knows that it is lagging. Or it can stall Santosh's read saying actually you have to wait till I replicate completely. There are different ways to solve that.
Okay.
Does that
Yeah.
Yeah, yeah, yeah. So I think some controller might be there for doing all this, right?
No.
Because replicas are stateless; they don't know the things.
No. Replicas actually are not stateless. Meaning, actually, Santosh's client is actually responsible to do all these things.
Yeah.
There is no
He will
controller
send the
there.
transaction ID. Yeah.
Yeah. So his application is whatever laptop or whatever he is using, right? That has a client in that is responsible to store this last transaction ID he saw. Other systems, the replicas doesn't care about what individual users, right?
Yeah. So this can happen and this can be solved in this way. This is really good. But in the Dynamo, I think you use that example for that shopping cart, right? So sometimes you go to some other replica, your items might go back and forth. But at the end, everything they give it to the user to resolve that conflicts.
Oh yeah, there actually you
Yeah,
can
that is
see
different.
items disappearing from the cart also, right?
Right. Yeah.
They
Yeah,
use
yeah.
eventual consistency. Yeah.
Yeah.
So I think they apply a model to basically offload this to client side. Like you are responsible now to handle conflicts and things like that, right?
Yeah. Because the client is the best person to know the conflicts and to
Yeah.
resolve it.
So
Yeah.
in this diagram, specific to this diagram, I have some questions. Like first of all, my question is, we saw that there can be a chance that inconsistency is there when we have equal to n, right? W plus R equal to n. So let's say 2 plus 2 is equal to 4. We know that it can lead to problems, right? So my first question is, what is the benefit then to set it even to a higher number, which is equal to n? Why just not set it to 1, right? Like, because is there some mathematical formula which will say that, okay, this much percentage your requests are going to be consistent, and this much time this much percentage will not be, right? Then why would even someone choose equal to n? Just select 1 1, right? Like W and R 1 1, and then that's it.
So your load will reduce, right? As you increase the number of replicas, right? I mean,
Sorry?
road will reduce single replica. Like if you keep only one replica, all the read traffic will go there, right? So if you increase it, then I think traffic will be distributed. That could be one of the reasons, right? Because anyways, stale data you'll get in both the cases. Or
No, I think I am misunderstanding. So you can still read from others, right? I am not restricting from reading from others. So I am specifically talking about acknowledgement, right? So you are asking two acknowledgement now from read. I am saying why not just set it to 1, right?
okay, so
You need
chances
to
of
increase
error.
the reliability, isn't it? So if you
Consistency
send it to
will
more,
drop. You
Mhm.
might get a
Correct.
stale
And
data.
Sorry?
Yeah, you
Your
will see
consistency.
time. Go ahead.
Yeah, go ahead.
No, I was
I'm
about to
saying
say.
chance.
Actually,
Go ahead. Yeah.
no, I was saying actually. Let's say you have all 5 replicas are there, right? Actually, you're setting acknowledgement for read and write to be 1, right? That's what you're saying.
Yes, yes.
Yeah, if that is the case, right? Actually, you write and actually replica 1 acknowledged it. Rest of the guys didn't get it. Now, when you read, right, your read is going to replica 5.
Yes.
That is a problem with actually if you don't have a quorum. In quorum, in the sense, there should be at least one overlap between the read and write replicas.
Yeah, that is thing. But one thing I think he
No,
is
but we just
asking.
saw that, right? 2 plus 2 also doesn't have any overlap. So I am
Yeah,
specifically
2.
looking for that
Yeah,
case.
2 plus 2 also have the same problem, right? So
Yeah. So if they both have the same problem, then why not reduce 2 to just 1, right?
no, at least
No, but
no. Then you have to go to the higher number, right? Not the lower number. 1 has problem, 2 has problem.
So if you
You'll
set
get
only
a-
one,
so-
if you write it to
Yeah.
that replica, and that replica fails.
Yeah.
So then you lose your data, right? So if you at least replicate to more than one, chances are that the second replica will have your data.
fault tolerant. Yes.
Okay.
Yeah, that is also one reason. Yes.
So more number of replicas is always good, but in some cases it's not possible. Then at least use one. So, but there are some drawbacks for that also. If you use only one, then chances are you might lose data.
I see.
And
Okay. This is a very valid point that I can just lose data. And how about read? Like, can I just not do read 1?
You can, but then you will read inconsistent data, stale data.
Which is
Because
fine.
all the
because
four of
getting into-
if it is fine for your application, it's okay. So read should be fine, but for the write might be a problem.
Yeah,
But
right.
if read-
Because it is data loss directly, right? You are compromising with data loss.
Yes.
That point.
Mhm.
And other point I had was in this diagram. Sorry, it may be a very newbie question, but I am seeing these cross section right? So does that mean that it is trying to write to 5 of them and 2 of them didn't acknowledge the write? Is that right understanding, or is it only writing to 3?
No, it's sending it to all 5 in parallel. 2, the X means actually the replicas didn't get that message. It is lost
Acknowledge
somewhere in
they
network.
didn't. Okay, it was lost. So I had then question that then is it not performance hit, like by just increasing replicas will also mean that I am writing parallelly to so many of them? Because I had an understanding that it will strictly write to whatever quorum we have decided. Or is it
quorum?
writing parallelly all of them?
No. Yeah, quorum will only for the acknowledgement. There is a line in that DDIA actually. If you scroll up, actually, summary is saying actually all writes are going in parallel to all the nodes. See, normally reads, that's the one actually, right above that diagram actually.
Okay.
Normally reads
So if we have, let's say, like horizontally 100 replicas or something, then what part does suffer because of these parallel writes? Like, will my writes will be slow or something, or
No,
this
no, the
doesn't?
bandwidth would be the problem, right? Actually, everybody is writing parallelly, sending everything, right?
Mhm.
This issue,
Your
right?
bandwidth, if you don't have enough bandwidth, then you will suffer.
But you will get consistent information, right? That's true.
You mean network bandwidth, right?
Yeah.
Yes. Yes.
Because I am assuming, like, let's say if this number becomes 20 or 25, right? Soon it will be like going to hit the ceiling, right? Like,
But yeah, so normally what is the size of the cluster, right? Actually, that is an important thing, right? So your cluster may be distributed to 5 data centers, right?
Mhm.
So let's say 5 data center, meaning actually each will have 1 or 2. Maybe the cluster size is 10 nodes actually.
Okay.
It could
So
be having 20, yeah.
yeah, in my experience also, I haven't seen like too many deployments more than 16 nodes. I am not even 6. Some people just do 8 or something. That's it, max. Because it comes with a management overhead also, right? Like, it's not easy
Exactly.
to cluster.
You normally put within a data center in 2 racks, you will put 2 nodes, right? Normally that's what I have done before.
Yeah. Okay, thank you. I think that solves my doubt, because I think that was important to not to miss, because this also will hit the limit if we keep on increasing the number.
Thanks. We also got to know something more. Yeah, that's cool. Yeah.
So yep. I think it's all comes down to your availability and consistency. What you are willing to let go and what matters the most you stick to. So correct, we were here, right? So these are the two situations.
So this kind of equation is valid for temperature sensors only, right? Where you don't need consistent information, even if still data is there. So average average is fine, right?
I'm
Like
just
W
thinking
plus.
loud. I just took some example. Maybe it
It looks like that
okay.
only, because there, even if you take still data, it won't cause much effect, right? While showing the temperature, because it's like average of a week, 10 days, like that, right?
Yeah, something like that. Yeah.
Or any
Because all the temperature sensors, they keep on sending the data. It won't go out for long. If it goes, then you'll have to find something else, right? Some other replica.
Yeah, I
Because
guess it's also.
Mhm.
Yeah, I was saying
Yes.
that it also gets down to the part, what is your frequency of read and write? Even though the number is small, if the frequency is high, I'm okay to lose the consistency in one of the reads because the frequency of read is high. So next read will eventually get it. I'm guessing might get the updated data. Frequency of reads are high. Just sorry, you were saying something.
No, same thing. Right? I was just trying to know any other application apart from sensors which use this equation, W plus R less than N.
Oh, all the systems, right? Actually, so if you use any dynamo-based systems, everybody uses something similar, right?
So their consistency is not much important, right?
So based on the usability, yeah, you will adjust this formula. Basically, for Amazon cart especially, right? Actually, you always see things disappearing, coming back up.
Yeah. And it's okay also there. It's not a big deal.
Yeah.
In fact, I would go that far to say that most of the practical systems out there are less than N or something like that, right? Like, if you even look at S3, it is definitely not greater than N, because you will have eventual consistency in and most of the AWS stuff for that matter.
But for payment system and all, it's not valid, right?
Yeah,
for
that's a different thing.
financial, it is strictly it doesn't make sense to have like weaker consistency models.
But I guess for S3 too, like if I am uploading my file, after some time I'm seeing, okay, my file is not there. I don't know like how comfortable I will be with that part.
So they always have this behavior. I think very recently they were saying we are doing the work for making it more consistent, but it is again today at present is the case that if you upload a file now, somebody at the other system, if he tries to watch the file, it may very well happen that he will not see or she will not see the file. That is the present behavior, and that is why you have to, most of the systems which are built on top of Amazon CLI or Amazon SDK, they do retries and find out, okay, if I have created a resource, whether I when I get the resource, do I get the value or not? And until then they do not call the resource as successful. That is how people circumvent this eventual consistency. Does
What
that
about,
make sense?
yeah, I have one question though. Suppose I did upload. I want to see like whether I have written that I should be able to see, right? Like how that is getting handled
I
in
think
this.
he's saying S3 doesn't handle, but your application should
No,
handle it.
yeah,
Client should handle. Yeah.
Client should
no,
handle it.
only the
You
client.
will you will keep on retrying until you see that desired value. Yeah.
Yeah, because if you make
Okay.
that thing in the S3 will be slower in response, right? So we don't want the lower layers to be slower. They should be faster in that latency. But the upper layers actually can take care of all those issues.
Yeah, so like
Because S3 has some other work to do more. That is more priority. Actually uploading the files and putting it in the right place, isn't it?
yeah.
So everyone's objective is different.
And read your own right, that model, how people are fixing it, like I understood that client does that. Apart from that, what all like the methods are there, like what all the solutions for that?
Yeah, your request will be always forwarded to the primary. So let's say the primary wrote your data, right? Then primary always will have your latest write.
Okay, so my request will always be routed there only, like I cannot.
Yeah.
Okay, so I will have some kind of session that my client knows, and from there I will be always routed there, like.
So to do that, right, what Facebook does is actually, so when you create a Facebook account, you will be pinned to, sorry, they will give you a home node actually, right? Home data center. Let's say you created your account from India and you moved to US, right? Still, your home node is still a data center near to India. All your rights will go there actually,
Okay.
right? So that way, actually, so that data center nodes always gets your rights actually, rights because that's where the right originated.
Okay, the first time I did create my account, right?
Every time, right? Whenever you make an update to your profile, you post something on Facebook, right? So they try to partition everything based on your user ID. So your user ID has a home location, home data center close to where you created it.
Okay.
It stays like that actually. So wherever you move, actually, so what they are saying is actually their system is highly optimized for reads actually, not for writes. Writes can take time, but that's understandable, right? When you post something, actually, you don't care actually. It may take a little bit time to post it, but actually, when you go to your home timeline and see your friends' messages, you want things to be faster there actually, right? Because what your action is mostly reads actually. You don't post a lot, right, as a regular user.
Yeah.
Yeah, makes sense.
So that is for writer. It's a sticky session kind of things they are doing.
Kind of, yeah. They are sticking you to not to one particular node. They call it actually home node or something like that. They combine couple of data centers and make it they call it as a region or something. So you're stuck to one region actually.
So are they taking from that region data from that region to the US? Let's say in India there is place called right where
Eventually, actually, so data is distributed within actually. So within a region, right? There are multiple data centers. The whole data for the Facebook will be present in one region. They will replicate it.
that
Let's say
means
there are
India's data can be present
Yeah.
in US data centers also, right?
exactly yes.
That will happen asynchronously, but on the fly it will go to first India region only. I mean,
Exactly.
the data.
Exactly. Yes.
Because they had that recent some issues with some countries not allowing data to be migrated, right?
Yeah.
So they
yeah.
do
I
that.
think European countries have some restrictions.
Yeah.
There. Yeah.
But it is done. Yeah.
But latency will also reduce in this case, right? Because if you redirect, if the write I mean, somebody is writing from India, right? And if that has to be accepted by the server in the US, latency will be more compared to that accepted by.
Yeah, but that
the
is only
server.
for the write, right?
Hmm.
Reads will be
Correct.
faster.
Yeah. So I think the news feeds are faster than posting.
Exactly.
Oh, yeah.
And only 1% of the people will be traveling or moving, right?
Hmm.
Rest of the people will still be in the same place.
Yeah.
Correct. This makes sense. So read your own write will be done by the master itself, which is primary, correct?
I think read your right actually that applies to that primary backup, no? Leader
Primary
and
the sense
follower. Leader and follower,
master.
not to the leaderless. But I don't know. Yeah.
There are
maybe.
a couple of ways to do that. One is actually you can always read from the primary. That makes sure that you'll always get the data, right? The other way is actually you can present the transaction ID to a replica.
So primary, you mean master, correct?
Master, yeah.
Okay.
The other way is actually, let's say you are connected to one of the close by replica, and you know actually as the client application knows what is the last write I made, the transaction ID of the last write. It can tell actually this is what I have done last. So that replica can make sure that it already has that data, or it can stall it, or it can reject that request. It's up to the implementation. Yeah.
Depending. That makes sense.
Yeah, that's good. Yeah. Thanks, Eric. Shashank. Yeah. Let's move.
Yep. Right. So moving ahead, with a smaller number of WNR, you're most likely to read state values because it's more likely that your read did not include the node with the latest value. On the upside, this configuration allows for lower latency, higher availability. Right. If there is a network interruption and many replicas become unreachable, there's a high chance that you can continue processing reads and writes. Only after the number of reachable replicas falls below WNR does the database becomes unavailable for writing or reading, respectively. So only after the number of replicas falls below W or R does the database becomes unavailable for writing. Yeah, because it's gone below. However, with W plus R greater than N, there are likely to be edge cases where stale values are returned. Interesting. These depend on the implementation. Possible scenario include, if a sloppy quorum is used, it's on page 183, the W writes may end up on different nodes than the R reads. So there is no longer a guaranteed overlap between the R nodes and the W nodes. Okay, I think I'm sensing there's some kind of difference in the network speed. Maybe that's why this is happening. Maybe. If two writes occur concurrently, it is not clear which one happened first. In this case, the only safe option is to merge concurrent writes. Again, write the clicks on 171. If a winner is picked based on the timestamp, last write wins. Writes can be lost due to clock skew. We will return to this topic in that page. Yeah, I think so. We saw that last timestamp or greater ID winner would be decided there. If a write happens concurrently with a read, the write may be reflected on only some of the replicas. In this case, it's determined whether the read returns the old or the new value. So saying if a write happens concurrently with a read, the write may be reflected on only some of the replicas. And in this case, it's undetermined whether the read returns the old or the new value. Okay, this is because it's happening at the same time. If a write succeeded on some replicas but failed on others, for example, because the disk on some nodes are full and overall succeeded on fewer inputs than W replicas, it is not rolled back on the replicas where it succeeded. This means that if a write was reported as failed, subsequent reads may or may not return value from that write. Okay, again, I'll read. If a write succeeded on some replicas but failed on others, right? And overall succeeded on fewer than W replicas. Okay, it is not rolled back on the replicas where it succeeded. This means that if a write was reported as failed, subsequent reads may or may not return value from that. So here it is saying it is not rolled back on the replicas where it succeeded.
Yeah, because it was
Uh,
half complete, right? It was half complete updating the replicas, and it could not complete the number of replicas required for acknowledgement. So it cannot roll back. It is very difficult to roll back, right? In this case, so you'll still have the latest data, but you cannot call that as a stale data.
Yeah. So in our case, let's say there was W equal to 3. Okay. And in that case, let's say 2 failed. Right was succeeded on some and others failed. So in that case, what happens? I mean, that one write happened is going to stay there. It is not going to roll back, right?
Yeah.
And there would be some read repair or entropy that will make sure that the other replicas get the data eventually. But in this case, this means that if a write was reported as failed, subsequent reads may or may not return the value from that write.
Because someone might read that updated value and some may not read that updated value.
Okay, that moment when it is not in sync or where the other replicas are down, that time. Okay. All right. If a node carrying a new value fails, and its data restored from a replica carrying an old value, number of replicas storing the new value may fall below W, breaking quorum condition. Interesting. This is something more like the read repair logic or the anti-entropy logic that we have that can address things. Even if everything is working correctly, there are edge cases in which you can get unlucky with timing. Linearizability and quorums on page 334. Okay, I thought this was something to do with sloppy, but no worries. We'll see that later. So interesting points. I'll just quickly cover them. If it's a sloppy quorum, things can go wrong. If writes are concurrently happening, the conflict happens, and it has to decide which takes priority. That's one thing. Just a second. Yeah, I should be back now. I hope I'm audible.
Yeah.
Okay, cool. Sorry, my VPN kind of what reset thing. So right, that was two things. The other thing is that writes and reads are happening concurrently. There could be a problem, and in that situation, also something fails, and the reads happen again. Inconsistency, and again when the read repair or the anti-entropy happens, when it's trying to restore the data, how it works out to make sure it has the latest data. And then obviously there's some timing related issues which we will see later on.
So there is strict quorum also, right? Or only normal quorum?
I did read that strict quorum.
Okay. I mean, okay, I may not remember exactly, but I have heard this term strict quorum. Oh, let's proceed.
Yeah. Yeah, let's see. So although quorums appear to guarantee that a read returns the latest written value, in practice it is not so simple. Dynamo style databases are generally optimized for use cases that can tolerate eventual consistency. The parameters WNR allow you to adjust the probability of the state values being read, but it's wise to not take them as absolute guarantees. In particular, you usually do not get the guarantees as discussed in problems and replication lag. Reading your writes, monotonic writes, consistent prefix reads. The previously mentioned anomalies can occur in applications. Stronger guarantees generally require transactions or consensus. Cool. I think we can stop here and then resume this part. It's or what do you guys say? Do you want to take this up now and finish it till here?
Yeah, we can stop. Yeah, no worries.
You can stop.
Yeah.
No problem.
See, if you go to line, okay, can you just go to page 179? Mudhir sir?
Yeah. Going to 179.
Yeah, and just slightly go down. Okay,
This page?
I don't think so. This is that page, right? So, what is the number of this page?
179. Here it is. This is
Which
179.
Yeah,
topic?
see, if you see at the last one, yeah, see, Shashank, you go slightly down where there is small 7 is written. Yeah, sometimes this kind of quorum is called a strict quorum.
Oh, yeah.
So if you
Yes.
see here what they are talking about, reads and writes, they obey R and W values are called quorum reads and all that. So that is what is calling as a strict quorum.
I think in grokking we read it, if I recall. Yeah. Strict quorum and sloppy quorums. Yes. Got it.
So the overlap is there, then it is going to be a strict quorum, isn't it?
Yeah. At least one overlap, right? Or is it like writing to every replica and reading also from every replica? That case would be very rare, right? Like writing to every replica and reading from every replica. Only in, I think, in payment kind of system you'll have those things. Very strict quorum.
No,
Leaderless payments financial won't actually go that route, I think so.
actually, I think
Go ahead.
no, I was about to say actually the strict quorum. What they mean is actually the whatever nodes we already set up, right, for that quorum is participating in the read and write. So for the sloppy quorums, actually, let's say one of the nodes or is down or something, unreachable or something, right? There will be other nodes within our cluster we can reuse in that node's place, right?
Oh, that is what hinted handoff is, right?
A hinted handoff is actually moving the data when the real node comes back up. First you form a sloppy quorum with an available data node or with an available node. You keep writing to because you want to satisfy the quorum for writes, right?
Correct. Yes.
Yeah, you keep writing the data into that node, but actually when you're reading it back, actually that node may not be participating in your read quorum. Actually, it will be accepting writes, and then when the real node comes back, actually it will take, actually I have this much data for you, actually you have to take everything from me. That is hinted handoff.
So hinted
Yeah, and
handoff
actually it becomes more prevalent when you use a consistent hashing ring. So at that time, you know, based on your hashing, this is a particular node addressing this hashing value. So you'll have maybe two of the replicas below it to be a quorum with that. And if in this 3, if one of them goes out, that will be a sloppy quorum. And then you will have a hinted handoff node actually will take care of that.
hinted handoff temporary node which takes on his behalf, which has failed, right?
So sloppy quorum is always coming with a hinted handoff.
Correct. Yeah.
So
So
when you introduce the consistent hashing into that, then there is some slight issues, right? Actually, consistent hashing, when a node fails, actually, so whatever data that node already had, right, that keys has to be redistributed. Here, actually, redistribution is not happening, my understanding. I'm not fully sure. But only we are using that extra node to keep writing data. Right?
Yeah. But they are actually this is also like a concept now, right? Because leaderless, if you do it, if you send it to all the replicas, then you will have a bandwidth problem. So it is always better to use consistent hashing. To maybe practical applications are like that, but this is just a conceptual wise, maybe a leaderless replication, which may be possible in some cases if you have a controlled number of replicas. But if
And
you, Mhm.
for the consistent hashing also, right? There is no requirement that actually you cannot write parallelly. So actually consistent hashing, anybody can write, right? Let's say the client can directly talk to, client can forward request to one of its close node, right?
Mhm.
That node can find out from its own information or from some location, it can find out actually for this key, these three are your nodes actually.
Mhm.
Right? And client can parallelly write to these three nodes, and or it can send it to a coordinator, and coordinator can do the same thing to the in on behalf of clients, right?
Mhm.
So it doesn't actually still you are writing parallelly to the quorum actually.
Yeah. So, but then you are writing to the only three of them. But in this case, what they are showing is in parallel, you are writing to all the 5 replicas.
Yeah,
You
because
are not following the strict sort of quorum wise, the number
yeah.
of replicas. Mhm.
So in our earlier case, in the consistent hashing, let's say your key is replicated to five, right? Nodes.
Mhm.
Same thing. You are writing into 5 nodes in parallel,
Mhm.
right?
Mhm.
So consistent hashing is just to make sure that, let's say, of that 5 in between one node failed,
Mhm.
then the next one in the ring will take over the some load of that.
Yeah,
table.
the distribution is much better in that case.
Exactly.
Yeah, got it. Yeah. But still, the problems are all going to remain the same.
Yeah, exactly.
Mhm. Makes
So,
sense.
so there are two ways, right? One is client is directly writing to the coordinator node, right? And second is client is writing to any other node in the ring, and that will find the coordinator, and then so there will be many hops in that case, right?
Only
Where
one more
client
hop.
Only extra one node.
Only
hop.
one hop. Yeah.
one hop. So, but how does client know which is? I mean, there are some cases where client directly writes to the coordinator node. How does the client
That
know
is the
that?
gossip protocol will actually get all the details of each and every node.
Exactly.
So, but
Yeah.
that will be among the nodes only, right? Not the client.
So client will come to any node. So gossip protocols update all this information to each and every node, and the client will read that information and then forward to the coordinator node. Is that node actually will do that?
Yeah, that is one way. That is actually there is no central authority for the how the nodes are arranged, right? Let's say you have a zookeeper node also, right? Who knows about the topology?
Yeah, the seeding nodes. Okay.
Yeah. So that zookeeper client can talk to zookeeper and ask actually for this key, what all are the replicas?
Coordinator. Yes. Else every node will have a routing table, right? Like if data comes, where do I need to route the
No.
data center?
Yeah, routing table. Then actually you are decentralizing things, right? Like gossip. Then it will be like gossip, right? If you bring in zookeeper, then clients doesn't need to know anything about routing and all, right? You are offloading all those work to zookeeper. Zookeeper keeps track of what all are the nodes for each key, right? The replicas for the each key. The nodes.
But I think in Cassandra you have routing table also. Every node keeps a routing table for this key, which all are the respective nodes. The data should be sent. No.
But actually, is there any zookeeper like network in Cassandra that keeps track of centralized? No, right?
I don't think. But coordinator node is there, yeah. But
Coordinator
there
is
is no.
coordinator is there. Coordinator has to find actually what all are the replica nodes, right? So
Yeah, I don't
Go ahead.
think there like all the nodes in Cassandra are basically treated equal, and every node will have the next two nodes as its replicas. So like if in the consistency hashing circle one node is there, then the next two nodes, depending on how many replicas you form for each node, right, it will treat the next two nodes in the consistency hashing circle as its replicas. And once the node when you talk about how the distribution is being done, or so they will have a set of distributed keys among the number of nodes. So because in the like how it calculates the like which node will handle how many keys is actually pre-decided. So once you add a node, it will redistribute all the keys. It will rehash the values, and it will basically sync the values from one node to another. This is, I mean,
So
this
for
is how Cassandra works.
that
Cassandra
is
is
so for
completely different.
that is okay, right? That is all the key distribution, right? How does actually Cassandra each node knows that the one what is the node above me and below me?
So above me and below me, right?
Yeah.
I forgot that
that is
name,
what
but like
routing table is there for that. if I
Exactly. That's what
recall.
I was saying. Actually, there are two ways you can do it, like gossip protocol. Then each node will have a routing table, right?
yeah, the gossip protocol is there. Yes.
Yeah. So that is one way. The other way is actually, let's say you offload all this work to a external node, right? Like a coordinator, zookeeper.
That's what happens in HBase actually. So
Oh,
HBase and Cassandra differ in this way. So
okay. Yeah.
HBase will have a master coordinator node which will handle all these things, like what keys are present in which node and like how to get there. Cassandra is like Cassandra in each node will basically will keep the information of its neighboring nodes and other nodes by interacting regularly with the gossip protocol.
Yeah. If you are not using the zookeeper, then in Cassandra, then you have to have this gossip, right? Every time you have to receive the heartbeats from the other nodes and make sure that they are up.
Yep. That's how basically it determines whether the node is down or not, and whether we need to handle that responsibility of reading it like and transferring that like maintaining that replica. So let's say there are 3 replicas for each of the node in a Cassandra consistency hashing circle. Then let's say one of the node goes down accidentally. So each of the like nodes from the gossip protocol will get to know that node is down, and because you can like read from any node. Let's say like if you have configured Cassandra to read from a client. Let's say you have written a Python or a Java client, and that needs to read. So it will try from any node. It can like the client can try from reading from any node, and it will like that node will take the responsibility of redirecting that read to the target node. So it can read from either the master node or the replica nodes. So let's say the master node goes down, then like the gossip, like through gossip protocol, they'll get to know, and then they'll maintain that like extra replica for that. So they will create a master node and redistribute the keys again, so that 2 replica thing is maintained always, like 1 master and 2 replicas for each of the node. So they will rehash and redistribute those keys among themselves till the node comes back. And once the node comes back, they will again do the same, and through like this hinted handoff, they will like push over all the keys which were written or all the values which were changed during the time when the node was down.
So is there any concept of master in Cassandra? It's a leaderless, right?
Yeah, it's leaderless. That's why all the nodes are treated equal.
So
Equally, okay. Accept the rights.
you can think similarly for the GFS, right? GFS actually is similar to Cassandra in that actually, but they have a what do you call as a master, central or master or something, right?
I think we did it a couple of weeks back. Somebody took GFS.
Yeah. So basically, think that master node or the central node zookeeper there, right?
Okay. Yeah. So client takes information from master, and based on that, it talks to the servers, right?
Yeah.
Like which file is presented. Okay.
Exactly. Basically, you can have 2 approaches. One, like Cassandra, everything is decentralized. Everybody knows about everybody. And or you can follow this GFS model. One person, the master or the zookeeper, knows about everybody, and everybody contacts through this person.
So in that case, in GFS, if master fails, there are some ways, right? Like
no, that's master is a coordinating node, no? It's a coordinating service. So yeah, maybe.
So metadata it is having, right?
Yeah.
Master node, right?
So that will have
So
its
if
own
that-
replications and all that, yeah.
So what I have read is that like in case where there is one master or the coordinator node, and like it is handling all the things to redirect everything. In that case, there will be replicas for that master, and there will be a considerable amount of a very little downtime. I mean, it can be from ranging from a millisecond to certain seconds, like in that replica switch, like where the coordinator node is actually switching itself from the master to the replica, because zookeeper will get to know, like, or like in case the zookeeper is not there, like in zookeeper there will be leader election protocol and all those things, but there will be considerable amount of downtime in that
No,
case.
so basically the pattern is actually, let's say you want to give redundancy or the fault tolerance for that master node, right? Or the coordinator node. You have to run a consensus protocol. So Zookeeper is running ZAB actually, Zookeeper Atomic Broadcast Protocol, or you can run Paxos or Raft in between.
Yeah.
So you have to run just to make sure that you're providing fault tolerance to the coordinator node. In GFS, what they do is actually they do a master sum approach actually. So whenever you make any metadata change, the writes is accepted at the master one, and it is replicated to the shadow master, and then only after the shadow master applies only, then the client will return a success response. It's synchronous replication there. Actually, they didn't do the consensus there, but actually you can still do the consensus, like a Raft or a ZAB or anything you can do.
Yep, makes sense.
Cool. Makes sense.
Yeah, that was a great discussion. Yeah, thanks, thanks, Eric. Yeah.
Yep. Thanks, Eric. Thanks, Lance. Thank you, everyone.
Thanks, guys.